Okay, so hello and welcome back. So in this video we want to get to the rest of these exercises, exercise 1.3, and the last one that we did was number 5. So let's see what is number 6. So number 6 is 202. Number 6 is show that f from, so f is a function, and you want to show that, you want to show that f from -1 to 1 from this interval to r is 1, 1. Which is given by f of x is equal to x over x plus 2. And the second part of this question, you want to find the inverse of basically f, which goes from -1, 1 to range of f. Let me write it as range f. Okay. So So first of all, these functions are interesting in that basically they are rational functions, and with these rational functions you get asymptotes. There is something called an asymptote. And there are two types of asymptotes: horizontal asymptote and vertical asymptotes. So for example, with this function, you can see that f of x is equal to x over x plus 2. Over here, x cannot be equal to -2. X is not defined at -2. You would be dividing by 0 at -2. So at -2, when the function basically when x gets close to -2 from left and right, what happens is that your function gets either goes to positive infinity very fast, or goes to negative infinity very fast, which gives rise to the idea of the asymptote, meaning that the asymptote is actually something like this. For example, you have -1 and -2, and then you have basically a horizontal line like this, vertical line like this, and of course you know that your function goes through 0, 0, because when x is equal to 0, then f of 0 is equal to 0 divided by something which is equal to 0. So your function goes through this point. Now as you get closer and closer to -2, from the right, for example, getting closer and to -2 from the right, you would have, for example, f of 2.1. So when x is equal to 2.1, then f of 2.1 is equal to basically 2.1 over 2.1 plus 2, which is equal to 2.1 over 4.1. So this must be something around 0.5 as far as I know. And if I get closer to, I'm sorry, I'm supposed to get closer to negative 2.1. I'm sorry, I'm supposed to get closer to negative 2 actually. So, so if I get closer to negative 2, then so negative 1.9, for example, or so if I try, for example, negative 1.1, I'm getting closer to negative 2 from the right. So that gives me basically f of negative 1.1 is equal to negative 1.1 over basically negative 1.1 plus 2, which is equal to negative 1.1 over 2 minus 1.1 is equal to 0.9, right? 0.9. So you can write this as basically 11 divided by negative 11 ninths, which is something negative 1 point something. Calculator here. So you have 11 divided by 9, which is about 1.2. Which is about negative 1.2. Now, as you can see, as I am, so if I get a little bit closer to negative 2 from the right, I would have, for example, suppose that, for example, you calculate f of negative 1.5, for example. That would give you, for example, negative 1.5 over negative 1.5 plus 2, which is equal to negative 1.5 over 0.5, which is equal to negative, 15 divided by 5, so that's negative 3. So as you can see, the value of your y is getting smaller and smaller as you're getting closer and closer to negative 2. That means that, for example, for negative 1.1, your output is at about 1, about here. But then for negative 1.5, your output goes to negative 3, which is somewhere over here. And the function goes through this point as well, and so you get the idea of an asymptote, which is something like this, meaning that the function tends toward this vertical line in this manner, but it actually never reaches to that point, to the line, because well, basically, first of all, the function is not even defined there. It is excluded from the domain of the function, and so you will get something like this. Right? Now, the next thing that happens here is that sometimes in these functions sometimes you have one asymptote, sometimes you have two asymptotes, a vertical and a horizontal. Sometimes you have several, for example, sometimes you have several, for example, vertical asymptotes. For example, in the case of periodic functions. For example, the function f of x is equal to tan x. The function f of x is equal to tan x gets those asymptotes periodically, because I think that this period of the tan function is pi, pi radians. So I suppose you go all the way up to negative pi by 2, you will get, this is negative pi by 2, this is positive pi by 2. I guess you get one asymptote here and one asymptote here, and then the function must be doing either something like this or the other way around. I'm not really, don't really remember that, but if I try f of x is equal to tan x well, as you can see, so this is this line over here. You can see that the function actually never reaches to this line, or maybe it does. I'm not sure. It's somewhere around. It's somewhere very close to this line. Now let's take it at this point. Let's take it at this point, which is something about 1, 2, 3, and 4. So this is basically each of these segments is, well, this is 2, so 2 divided by 1, 2, 3, 4 is 0.5, so this is 1.5, right? So 1.5 is the same thing as, what is that? So in terms of pi, if you go for pi divided by 2, pi divided by 2 is something very close to 1.5, 1.6 or so. So as I suspected, it's very close to 1.6, and again negative 1.6, and then the function is doing this periodic behavior between the two asymptotes, and this grapher doesn't give you those asymptotes. If you want to see the asymptotes, you need to use another graphing calculator, which is called GeoGebra Symbolab. If you use Symbolab, if you try f of x is equal to tan x, as you can see, it gives you the asymptotes as well. So here you have, for example, this is basically these red lines, these vertical red lines are basically your vertical asymptotes, and you have an infinite number of such asymptotes here. And also the good thing about this calculator is that it gives you those discontinuities in the function and in the functions as well, because these functions, what happens is that these rational functions do have sometimes discontinuities as well. Well, but I don't want to get over there. I'll get to that right now. Now, anyway, so that's all about asymptotes and rational functions. Now, what's important here is that this function gets another asymptote at y is equal to I suppose 1. At y is equal to 1, you get another asymptote here. And there is a reason for that, why that happens, which is actually interesting in terms of the inverse of the functions. So you see over here, this function gets an asymptote. You see that it tends to x is equal to -2, which is this vertical line here, and also basically the function tends horizontally to basically this line, which is y is equal to 1. So that means that I actually have to erase this part of the function and then have y is equal to 1 here, and basically draw these horizontal asymptotes, and then the function actually tends towards this line. Gets closer and closer, but never actually reaches that line, and then it does the same thing, and then it does the same thing over here. Kind of something like this. Okay. Now, so this is basically first of all the graph of the function and some information about the graph of the function. Okay, so the next thing that we want to find out about this function is that is if the function is 1, 1. We want to show that this function is 1, 1. Now, of course, you need to prove using algebra and that sort of thing that the function is 1, 1. But then again, it's also useful to understand what is 1, 1 in terms of the graph of the function, because it's not basically as easy to read algebra as it is to basically read the graph of the function. What I mean is that, for example, as you can see in this function, the output of this function is always distinct. All of the outputs of this function are distinct for distinct inputs of the function, and basically by input I mean this horizontal axis here, and the output becomes your vertical axis. Now, if you pay attention to what's happening, let me show you a better version of this function. Of course, that's not exactly the best way of looking at this. So if you take a look at the function now, you can imagine that there is an asymptote here at y is equal to 1. There is an asymptote here at x is equal to -2, and you can see that for every distinct point of the domain of the function, there is a distinct output in the codomain of the function, meaning that there is no 2 points in the domain of the function that have been mapped to the same point in the same element in the range of the function. Meaning that, for example, let's think about the function which is not 1, 1. For example, the function which is not 1, 1 is some function is of course many 1, right? So a function which is many 1 is by definition is some function that you have some x1 over here, and you have some x2 over here, and you have some y1 over here. This is your codomain, this is your domain. And x1 is mapped to y1, x2 is mapped to y1. And if I think of this as f, then f of x1 is equal to y1, and f of x2 is equal to y1. So this function is of course many 1, it is not 1, 1. And And then what happens is that if you do the graph of this function, you will see some point y1 in the range of or in the codomain of the function that has been mapped to two different inputs. Meaning that, for example, you can imagine that the output at 4, for example, would be for example 4, and the output at 6 would also be 4, right? So then you would get basically some function like this. So let's just say that this is 1, 2, 3, and 4. 1, 2, 3, and 4. So the output at 4 is equal to 4. That is 4, 4. The output at 6 is also 4. This is 6, 4. Now this is a function and there is no problem with it. And of course you can imagine that basically the rest of the function looks, for example, something like this. For example, this is one part of the function, and the function goes through this point and so on and so forth. It could have other curves and bends and everything in the function. But then this is basically what a function looks like, and in terms of the graph, if the function is many one. Two different points, two distinct members of the domain of the function are mapped to exactly the same element in the range of, or in the codomain of the function. So that is basically that, and of course that is not the case. That is not the case with this function. Now, now, of course, it's simple to calculate it's simple to show that basically this function is 1, 1. You see that the domain of this function has been limited to -1 to 1. Meaning that you go from -1 to 1, and that is basically the domain of your function. Right, so that is the domain of the function, and the range of f and the range is basic, or the codomain is basically the set of real numbers. So basically to show that f of x is equal to x over x plus 2 is 1, 1. And of course you know that f is a function from -1 to 1, to r basically, right? So to show that the function is 1, 1, of course you need to show that for every x1, y1, for every x1, x2, for example, for every x1, x2 belonging to the domain of the function, f of x1 is equal to f of x2 is the same thing, that implies that x1 is equal to x2, meaning that there are no two distinct inputs in the domain of the function that have been mapped to the same output in the codomain of the function. Now, if I make this assumption here, this is our condition, and if I make this assumption here that is the case, then I want to prove this for this function, so I'm going to assume that f of x is equal to, I'm going to assume that basically f of x1 is equal to f of x2. F of x1 is equal to f of x2. And so what that means is that then f of x1 is going to be equal to basically x1 divided by x1 plus 2. And that is equal to x2 divided by x2 plus 2. And now if I cross multiply, I will get x1 x2 plus 2 times x1 is equal to x1 x2 plus 2 times x2. And then you can simplify these two, cancel them out. That gives you 2 times x1 is equal to 2 times x2, and which means that x1 is equal to x2. So f of x1 is equal to f of x2 implies that x1 is equal to x2, which means that basically f is 1, 1. Right? Now let's take a look at the solution here. And there is also a hint here. Let me see. Let me take a look at the hint. It says that for y belonging to R, to range f, y is equal to f of x is equal to x over x plus 2 for some x in. Okay, so basically for here the solution is f from -1 to 1 to R is given as f of x is equal to x over x plus 2, and let f of x is equal to x to f of y, and so x is equal to f is 1, 1 is a 1, 1 function. That's basically one part. Okay, so the next part of this question, you want to find the inverse of the function. You want to find the inverse of the function. The function f f from basically -1 to 1 to range of f, and you know that f of x is equal to basically x over x plus 2. Right? Now, as we pay attention to this function over here, f of x is equal to x plus 2, you can see that the function is of course 1, 1. We have no problem with the function being 1, 1 throughout the whole domain of the function. The function is 1, 1. There is no problem with that. But the function is not on 2, because as you can see, for example, there is this output here, y is equal to 1, which is basically not the image of any element, which is not the image of any element in the domain of the function, and as a result you have gotten this horizontal asymptote here. So of course throughout the whole range of the function, or throughout the whole basically codomain of the function is not on 2. But the question that has been asked here is we want to show that we want to find the inverse of the function, basically f from this domain to this range, and the range of f is basically not the whole codomain of the function, but only a part of that, meaning that basically, as you can see, f goes from this point over here all the way up to probably this point over here. So this part is the range of f. Apart from that, the rest of the codomain of the function is not a part of the range of f, of course. So what that means is that then throughout this domain and throughout this range, the function is onto and 1, 1. So the function is, you can find the inverse of the function there. There is no problem with that. Which means that basically, when you want to find the inverse of the function, first of all, you have to make sure that the function is 1, 1, which we have already established. And also you need to show that basically f from basically -1 to 1 to range of f, having f of x as x over x plus 2, that this function is onto as well. To show that this is onto, what you need to do is that you need to basically, you need to show that for every y belonging to this range, meaning that all of the y's belonging to this range is the image of some element in the domain of the function. So in order to do that, you can use the inverse of the function, meaning that if I write f of x as f of x is equal to x over x plus 2, and write f of x as y. So if y is equal to x over x plus 2, and if I cross multiply here, I'll get x times y plus 2 times y is equal to x, and find x in terms of y, meaning that I can write xy minus x is equal to -2y, or I can write x minus xy is equal to 2y, which means that, and then if I take an x out here, then 1 minus y is equal to 2y, which means that x is equal to 2y over 1 minus y. And what this means is that, now what this means is that if you give this part 2y over 1 minus y, if you give it to your function, it will give you a y. You see over here f of basically 2y over 1 minus y. What happens if you give it to your function is basically you will have 2y over 1 minus y over 2y over 1 minus y plus a 2, right? And if you calculate this, what you will get is basically 1 minus y, 2y, and then y minus 1 minus y, 2y plus 2 minus 2y. And these two will be cancelled out. You will have 2y over 2, which is equal to y. Which means that f of 2y over 1 minus y is equal to y. What that means is that for every y belonging to the range of the function, or to the, what you could say, codomain or range. Of course, you need to know how you're using the two words, in what sense. But you can say that generally there is a there is a mechanism that can get you to any y in the range of the function, and that mechanism is 2y over 1 minus y, right? Now, except that if y is equal to 1, then there is a problem, meaning that, as you can see here, y is equal to 1 has a problem over here. Other than that, you have no problem any y in the codomain of the whole function. Even you can get back to that as long as you enter this 2y over 1 minus y into the function. Now over here what we have is basically our function is defined from -1 to 1 to the range of f, right? So we said that basically for every y in the, let's say in the range of the function that we are talking about right now, which becomes ultimately the range of f, for all of these y's, there must be a mechanism to get us to that y, which means that I need to know whether y is equal to 1, which is restricted here, whether that y is present here or not. If it is present, then the function in this, having these conditions, is not onto, otherwise it is onto. Which means that now I'm simply going to test whether what is the range of this function under these conditions. Now the range of f is basically we have f of x is equal to x over x plus 2, and you can basically calculate f of minus 1 and f of 1 and see where that gets you, meaning that f of -1 is equal to -1 over -1 plus 2, because the function is x over x plus 2, which is equal to -1 over 1, which is equal to -1. And then from this point, as you can see, that the output of the function is increasing and increasing until it gets to x plus 1, right? So f of 1 is going to be equal to 1 over 1 plus 2, which is equal to 1/3. So you would never get to y is equal to 1, so you have no problem there. And the only thing which is restricted here is y plus 1. So here y is not equal to 1, and that is the only restriction that you have. But as you can see, you actually never get there. You start from -1 and you go all the way up to 1/3, and that's all that basically this function is all about. So you can say that based on this, you can say that it is clear that f as a function from -1 to 1 to range f is onto, right? Is onto. Therefore, and previously we showed that basically the whole function f is injective or 1, so we can say that the function f from -1 to 1 to range f, is 1, 1 and onto, and therefore the inverse of the function the inverse of the function f from -1 to 1 to range f exists, right? So now in order to find the inverse of the function, what you need to do is that, for example, you can say that let some function g from the range from the codomain to the domain, meaning from range f to this interval, from range f to -1, 1, be the inverse of f. And let y be an arbitrary element of range of f. Let y be an arbitrary element of the range of f, f, of course, I'm sorry, the function for which we are finding an inverse. Now, since f is a function from -1 to 1 to range of f, is onto, we have y is equal to f of x for some x belonging to -1, -1, which means that basically of course whatever sort of y that the range of f, if I take the range of f as over here, we have taken y to be an arbitrary element of the range of f. So whatever element y that I have in range of f, there has to be some element basically belonging to this set that gets you to that element, right? That is the pre-image of that y in the range of f. And hence this is statement y is equal to f of x for some x belonging to -1, 1. So then you can say that y is equal to basically y is equal to x over x plus 2, and if you do the math and all of the algebra that we did over here, we will get to this expression here, or this equation here, which is x is equal to 2y over 1 minus y, right? So that gives us basically x is equal to 2y over 1 minus y. and here y not equal to 1, of course, right? And so now let us define g. Let us define g as from the range of f to the interval -1, 1 as, for example, g of y is equal to 2y over 1 minus y, or y is not equal to 1, and now in order to show that this function is actually the inverse of our original function f, we need to show that basically GOF of x is equal to I of x, and we need to show that FOG of y is equal to I of y, meaning that, let me write another step here. Now, in order to show that 1 is the inverse of basically this function that we were talking about here, which is this, hopefully we can find it, this function here, which is f here, right? Now I know that my notation here is a little bit messy, but I'm showing you what I exactly mean, so I hope you don't get confused, because this function up here is also f. So but what I mean by f right now is basically this function here, right? So now in order to show that 1 is the inverse of f, we need to show that GOF is equal to I of x, and okay, so now we said that now we have found this function. Now in order to show that this function that we have called 1 here is actually the inverse of f, we need to show that basically GOF of x is equal to I of x, and meaning that GOF is basically the identity function on the domain of f, meaning that the domain of f over here as we had it is basically all of these elements. We have called that x, or I of x, meaning that whichever one of these elements, if you give it to this function GOF, it will give you the same element. That is basically the identity function on the domain of x. And you also need to show that FOG is equal to I of y, meaning that FOG is the identity function on the codomain of f, meaning that codomain of f is basically all of these elements over here. The range of f, becomes, in this case, the codomain of f. Of course, I should have called this, for example, this f refers to this function that we had over here, right? So I should have called this, for example, I don't know, the function h or something else, but then that second f refers to this function. But this whole thing, range of f, which is range of that function up there, it becomes the codomain of this function f, of course. Now, what that means is that FOG is basically I of y, which means that the identity function on this set, whichever one of these values, if you give it to that function, it gives you the same element back. And we have basically talked about this, why basically that happens and why that is important and necessary. So so now, in order to show that both of these are true, then I simply calculate GOF of x, for example. So GOF of x is equal to basically G of f of x. Now, f of x is basically, let me write down this function. F of x is equal to x over x plus 2. Write it over here. F of x is equal to x over x plus 2, and f is a function that goes from basically -1 to 1 to range of f. -1, 1 to the range of f. Okay, so what that means is that then GOF is going to be equal to, basically in the function g, wherever you see a variable y, you have to put, this is the same thing as g of f of x. You have to put the function f of x. So this is equal to basically 2 times x over x plus 2. And then we have 1 minus x over x plus 2. That is the same thing as 2x over x plus 2 over x plus 2, and 1 times x plus 2 is equal to x plus 2 minus x. These two will be cancelled out, and you have 2x over x, which is equal to x, which is equal to 2x over 2. You have 2x over 2. You have 2x over 2, which is equal to x, which means that basically GOF is equal to basically GOF of x is equal to x. That means that GOF is equal to I of x, meaning that whichever one of these x's that is the input into the function x, that is input into the function f, if I give each and every one of those inputs into this function GOF, I'm going to get the same thing back. As you can see, GOF of x is equal to x. And this x represents any input into this function from that set, of course. Which means that I can say that GOF is the identity function on the domain of f, or the identity function on the set x. Now, I also need to show that FOG is equal to I of y. And so FOG of y is the same thing as f of g of y, right? And g of y is basically this function here. F of f is this function here. So that means that in f, wherever you see a variable, you have to put the function g of y, which means that you have basically 2y over 1 minus y, and then again 2y over 1 minus y plus 2, which gives you basically 2y over 1 minus y over 2y, or basically 1 minus y, 2y plus 2 minus 2y, and these two will be cancelled out. These two will be cancelled out. You have 2y over 2, which is equal to y. So what that means is that any y that I input into this, any y which of course belongs to the range of f, or the codomain of this function f, any y, if I input it into this function f of fog, the function gives me the same thing back, which means that fog is the same thing as the identity function on the set y, or this is capital Y, which is basically range of f. I write it as I of range of f, right? I of range of f. So, and therefore you can say that g of y is the inverse of f of x. Is the inverse of f of x. Or you can say that the same thing, you can say it as f inverse is equal to g. Right, so this was question number 6. This one is a pretty important question, because the function is a little bit complicated. It has all of these asymptotes, and you have to decide all of these things. And but I suppose you have understood the whole story from the beginning. I hope so. Anyway, so I thank you for watching this video. I'll see you with question number 7 in the next video. Thank you.